Welcome all. I'm Makena. I'm a data engineer at EMSL, and today I'm going to talk about how to deploy AI tools at scale. So this is after you've built a great LLM-based application, like some of the other presenters have shown, how do you actually deploy it so that you can handle multiple interactions at the same time, things like that. So here's an outline for the talk today. I'm going to start talking about self-hosting LLMs. And also talk a little bit about open source large language models, because that's really, you learn some of the basics for how to deploy at scale by self-hosting. Then I'll talk through hardware requirements, so figuring out, which open source models can you host given your hardware. I'll go through some other technologies and concepts that I think are helpful. Then we'll look at containerization. So that's sort of the first step of deploying somewhere is containerizing your application. Then I'll talk through some basic CI/CD and security basics. And then I'll wrap up with some current efforts related to Science Central and the BER integration effort, and also talk through some emerging technologies that'll become more relevant in the future. So to start, I'm gonna talk about Docker. So Docker is a great technology to use when you're looking to ship something to production. And the reason is it's got basically a write once, run anywhere that Docker is installed um, feature. So if you've got Docker on your local machine and you're able to run your application in Docker locally, then you can be assured that it'll work the exact same way on some other machine. So that means you basically one place and then you can ship it to any sort of deployment infrastructure that you want to. There are also tools for like sharing applications that you've written, and we'll look at some of those today. This image is Docker Desktop. This was a screenshot I took of mine because I use it personally every day for work. Okay, so the next thing I want to discuss is Ollama. Um, Here are some instructions. This isn't a workshop, but this deck will be available if you want to try some of these things out yourself. Ollama lets you self-host LLMs. There are other ways to do it. Ollama is just sort of a beginner-friendly way. So you just download it. You can pull a specific model. So here, this would pull Llama 3 latest. If you do Ollama list, it'll give you the models that you've pulled and installed locally. So you can see on my local machine, I have 4 models, and it shows the size of each one as well. The other thing to note is running Ollama bare metal, which means not inside of Docker, provides better performance typically. And this is because Docker can't always take advantage of GPU hardware. So especially if you're running like an M1 type Mac, you'll see significantly worse performance running Ollama and Docker than you would running it directly on the M1. And so just basically, once you've pulled an image, you can chat with it directly, or you can use the Ollama serve command to put up an API that you can use for all kinds of things. Okay, so the next step and the next thing I want to discuss is Open Web UI. So Open Web UI gives you sort of a front end for Ollama, and it gives you an interface similar to like ChatGPT or Claude or any of the sort of frontier models. So it's got things like chat history. You can perform basic RAG by uploading documents. You can try out multiple prompts. Another nice feature is you can send the same prompt to multiple language models at once to basically test the performance in real time. So it's a great tool to sort of start building things and testing things out, like basic RAG, basic prompt engineering, things like that. Um, Here's the command to run it. So we don't need to discuss every argument here, but basically this is the image it's pulling. This is the official Open Web UI image. And then it's got some other things like you want to restart it, gives it a name, creates a volume for it, where it can store the chat history. And then it'll be available on localhost 3000. And if you've got Ollama installed and running, it'll just connect right to it automatically, and you can just use it right out of the box. Okay, the next thing I want to discuss is hardware requirements. So now you know how to get a model onto your machine, but which models can you actually host with some decent performance? One technique that you can take advantage of is a technique called quantization. And this is sort of an oversimplified look at how that works. Uh, Here we've got a representation of a full fat large language model, which means it's got full precision weights and biases. Now, one thing we can do in order to save space is quantize it, which basically means rounding the weights and biases. So in this case, we go from 0.7754 to 0.78. So we've reduced the size, we've reduced the amount of precision without throwing away the value. So what this means is you maintain a lot of the behavior just at maybe a less precise, just with a little less precision. And so typically full precision, you use 4 bytes per parameter. Then the first level of quantization is called 16-bit quantization. That's 2 bytes per parameter. So that means you're having the space requirement. And then 8-bit is doing the same thing again. So having it again. You don't really want to go beyond int 8. I mean, there is int 4, but it's generally agreed that int 8 is the limit for when things are still working. But it's always best to try these out yourself and see how it works. Okay, so now we know a little bit about quantization, but that still doesn't answer which models we can run given a particular GPU or TPU. So I've linked this calculator that you can use, and I've got the basic calculation here. It's basically how many bytes per parameter, so that depends on the quantization, and then the number of weights. And then you have to add to that the key value cache, which can change depending on the context length of the model. And then a framework overhead, which is like the overhead for something like Ollama or VLLM that we'll talk about later. But rather than, using this, just find a calculator and use that. Okay, next we're going to go into some like helpful technologies. The first is Fast API. So Fast API is a library that you can use to build APIs in Python. API stands for Application Programming Interface, and it's analogous to a UI, which is a user interface, except that rather than a user being like the intended consumer, it's an application that's the intended consumer. So this is a way for software to do some of the same things that the UI does programmatically. And this is really helpful because it allows you to connect different pieces of software together. This is used most often connecting a front end to a back end. So if you want to deploy an application that's not just using Streamlit, maybe you want to use React or some other front-end framework, then you would need some kind of API to expose that to the front end. So this is a really core piece. If you're not working in Python, there are other libraries in other languages. Fast API is just my favorite in Python. Next up is vector databases, which were touched on in some of the other talks. Chroma is one that's popular. Also, Elasticsearch has a vector database. Even Postgres has an implementation. But the basic idea is you have a series of documents, you chunk them up, you embed the chunks, and then anytime you get a query, you do the same thing. You embed that query and then find all of the documents that are most similar to that query after they've been embedded. And then you just grab the contents of those documents and shove it into the prompt for the LLM. So you say like, answer this question, you put the question given this context, and then you put the documents in there like that. And that's helpful for just adding like domain-specific knowledge. Okay, another thing I want to touch on is VLLM. So we don't need to go into the details, but VLLM is a way to scale up from Ollama to something production ready. And I've linked the paper here. You can read that if you're interested, but basically what it does is it's got a technique for managing concurrent requests and then scheduling them out to the various LLMs in an efficient way. So they can handle multiple concurrent requests without just falling over. If you try and make multiple concurrent requests to Ollama, it doesn't have this technique, so it'll just put it in a queue and you'll just be blocked until the LLM is available, basically. So this is a great technology if you're wanting to self-host for a production-ready environment. Okay, so now we're ready to jump into containerization. The first step of containerization is to create a Docker file. And a Docker file creates what's called a Docker image. So I've got an example here, which is a basic fast API Docker file. So you can see I'm starting from the Python base image. I'm starting at the app working directory. I copy a requirements.txt into my app directory. I install those. Then I copy the rest of the contents into the app. I load the data using this command here, and then the CMD special word says like, this is how you actually start the application. So in this case, we're doing two things, right? We run a little script and then we run fast API. So this is sort of one service. And you notice that in contrast to like a Conda environment or a virtual environment, this has all of the steps to install and run the application. So it's everything you need to actually run it somewhere. So once you've got your Docker file, then we can talk about how to compose Docker images into containers. So here's a Docker compose file. This is for a real project, and it's using a lot of the things that we discussed. So the basic structure is you list your services. So I've got an API service. That's the Docker file I showed in the previous slide. I've got a doc search, which has a different Docker file in a doc search directory. I've got an agent template, which is this particular project is to show folks how to combine agents together into like a multi-agent framework. I've got an Ollama locally that's just for basic encoding to build my Chroma DB. And then I've got a Chroma service. So this Chroma service can be shared across the other services as well. And the way I get all of these services to talk to each other is I put them all in the same network, which I called app network. Um, I port forward when necessary. And then finally, you can use this depends on to define the order in which things need to be built, right? So Olama is the first thing that needs to be built because I use it for that load data step that was in that other Docker file. So then to run something like this, you do a Docker compose up and it'll build all of these services and then spin them all up together. And this Docker compose.yaml, once you have this along with the rest of the repo, it's ready to deploy basically anywhere that Docker is installed. So now that we've got it fully containerized, let's talk about the basics of CI/CD. So CI is continuous integration. That means basically anytime you push to a repo, you want to do a test build. Um, and that basically says, hey, look, if the Docker file or the Docker compose won't even build, then we won't allow this change to get into production. Then you can run automated testing and do all of that before you do a merge. So this is like a script that runs anytime a merge request is created. Continuous delivery, there are different methods for this, and you should work with your whoever you have for DevOps to figure out what works with your environment. We use GitLab and Helm for our deployments, but it depends a lot on which context you typically deploy in. And then continuous deployment is just a way to typically you create the image, put it into a container registry, and then have some kind of Helm chart that deploys that image. For security, I wanted to highlight Dynaconf. It's another Python library that lets you define settings, and it's got a built-in way to manage secrets, and it works well with CI/CD variables. So you can set those securely in your repo, and then as it's being deployed, it will overwrite some of the settings in that are defined in your Dynaconf files to be the like actual true secrets. So with that, I've covered basically all the basics of how to containerize and deploy these types of applications. So now I'm going to switch over to some of the current work with Science Central, as well as the BER integration. So here are some tools that we've launched. Science Central is sort of our all-in-one platform. It's got places where users can spin up Jupyter notebooks on our infrastructure. You can explore our data. You can submit a proposal. If you're internal to the network, we've got guru.emsl.pnl.gov, which is a deployed open web UI instance with a few different models in the that are supported on the back end. We'll be launching LLM-based search this year. It'll include a couple tools, one written by me, one written by Gihan. And then going forward, we'll be integrating more and more of these agentic tools that you've seen today with Science Central, making them part of our tools for users. Next is the BER data integration effort. So there are these different institutions across BER that each handle different parts of biological and environmental data. And there's an effort that's been underway for over a year now to harmonize our data and make it so that you could essentially make a single API call to sort of a consolidated API that would give you results from all the different resources. So NMDC, JGI, ESSDive, and EMSL. And we've already got that API up and running. We're going to be improving it later this month. But here's an example of some work being done in a Jupyter Notebook. And you can see we've searched across all of the BER resources and found samples that it's actually the same sample across all of them. And then you can do things like geospatial queries. You can look at different metadata collected for samples across the different resources. Next, I'm going to talk a little bit about MCP. So this is a newer technology developed by Anthropic. What it allows you to do is it's sort of a standard for how to interface with different resources. You'll notice that it's in this image, which is provided by Anthropic. It's mostly local. So MCP is designed mostly for local tools, like maybe your calendar app running on your machine. In the future, there's an idea that there'll be more integration through web APIs. So that's, in a way, this is thought of as the future of APIs for these agentic systems. But it's still the Wild West, and all of these things are, very new and experimental. And then beyond even MCP is A2A, which is the agent-to-agent framework, which Google developed. This has almost no adoption yet because it's so new, and there are so few agents in production at the moment that this just isn't being heavily used, but it's something that may show up in the near future. And with that, I'd just like to acknowledge my team. Ratna and Evan helped put a lot of this stuff together. They've helped provide the vision as well as some of the CI/CD work to get some of these tools online and I've and also the developer proposal 61408 that all of the presenters today were on. And yeah, I'm happy to take questions, and there's my contact as well. So thank you.
Thank you very much, Makena. Great presentation.
Thanks.
Does anybody has questions here in the room? In the meantime, I have a question. So is the Guru link, the server, is it available externally too?
It's not available externally. We're working like in real time on something that will be externally available.
So thank you for the presentation. So the other slide, you're talking about containerization and creating a Docker image. What about like if you want to kind of use it in a Conda environment, is it also going to be available? Because I know like for most of the scientists, sometimes they want to run it like on a large database. Maybe they have a lot of samples or something like that. And instead of just using they just want to like download the Conda environment and run their samples without having to like creating a Docker image or something like that. I don't know which one is actually better, but I'm just, like trying to ask about the fact that some of the scientists are much more familiar with the Conda environment than Docker images. So I don't know.
Yeah. Yeah, so I'll go back to that one. There are ways to use Conda within Docker. So here I'm using you can imagine like a virtual environment set up in Python where you put all of your requirements into a requirements.txt file. You could do something similar with Conda. In the typical like Venv framework, you can do something like pip freeze and then put those into a requirements.txt file. There's something similar you can do in Conda, but the the power of Docker is that any place that's got Docker, you can deploy to. So that could be the cloud, it could be a Kubernetes cluster, which is what we do here a lot. It could be some virtual machine somewhere. But really my recommendation is if you're not familiar with Docker, don't be afraid of it. It's actually very simple. It's basically just a list of steps. And the other advice I'll give is things like ChatGPT and Claude have been heavily trained on Docker files and Docker Compose files, so they're very good at answering questions about them. So you like, for example, if you said, build me a Docker Compose that has, these 5 services, it would spit out something that's very close to right, usually. It just takes a little bit of know-how about what to ask for, I guess.
Hi, thank you for the presentation. I have just a simple question about quantization slide
Sure.
when you
Yep.
show the networks. Yeah. So my doubt is when you have very low values, so let's say that they are closer to 0. So when you round off to 2 decimals, so you are going to get all of them zeros. So how do you handle that, or is that matter?
Yeah, so the one important note is that this is a very oversimplified view. In reality, we're going from 4 bytes, which is, I think each byte is 16 bits of precision. So that's 64 bits down to 32. So it's not really like 4 decimals to 2. It'd be more like 64 decimals down to 32. So even pretty small values are okay. But that said, that's why it's also important to test these things, because it's not out of the box obvious that you'll be able to retain the same behavior when you throw away some of this precision.